Reinout Quispel from Trobe University, and he will be talking about discrete Darboux polynomials and preservation of measure and intervals of ODEs.
Thank you very much. I'm very happy to be back here at the Isaac Newton Institute, and I'm particularly happy that my talk has been scheduled in the Young Talent session. But kidding aside, I'm also grateful to the Simons Foundation for supporting my visit here. And my aim will be to give you a bit of an introduction to discrete Darboux polynomials, what they are and what they are good for, how do you find them, etc. But before I do that, I think I have to explain first what Darboux polynomials for ordinary differential equations are. So this is the outline of my talk. The first part I will try to explain what the sort of definitions and so on of discrete Darboux polynomials. And in the second part, I'm going to give you some examples which involve the Kahan discretization. So these are examples in the numerical discretization of ordinary differential equations. Okay, so start with part one. And by all means, do stop me if I go too fast. My aim will be not to go too fast, but if I still do, let me know. Okay, oh yeah, I should also say those in the very last row maybe come forward one or two rows because some of the slides may be hard to see from the back. Okay, so what's the aim? The aim of this talk will be how do you find rational integrals of discrete rational maps. So you can think of discretizations of differential equations, and this will hold for differential equations that are both, or that are either integrable or non-integrable. That doesn't matter. But these are sort of two different areas of application, if you like. And as I said, before we go to the discrete case, let's look at the continuous case, which of course, as will not surprise you, was introduced by Darboux. Now this is not to be confused with Darboux transformations or Darboux's theorem. This is a separate issue which is actually generally less well known. Okay, so if you have two polynomials P1 and P2 in arbitrary number of variables, then their ratio is a rational first integral of this differential equation, the xct equals f of x, if this p1 dot times p2 minus p1 p2 dot equals 0. So this is of course just if you take the derivative of p1 divided by p2, this will be the numerator, and if we assume that of course that the denominator is not 0 everywhere. For a polynomial ODE, if you want to find P1 and P2 from this equation, of course that will contain the coefficients A in P1 and the coefficients B in P2. So it's a bilinear problem. What we're looking for is a linear way to solve this problem. So Darboux came up with such an idea, and that is now we have two kinds of polynomials, P and C. Then the polynomial P is called the Darboux polynomial of the polynomial ODE. So we assume the ODE is polynomial at the moment. If the derivative of P is C times P. Of course, if C is identically 0, then P1 is what's called the first integral. But if you have such a function, so that this is the this derivative here. Now, I should say, of course, what you do here is that you for x dot you substitute this. So this is on for solution of the differential equation. So that P dot is a multiple a polynomial times p. And this c in front here is called the cofactor. And these Darboux polynomials, they also go by many other names. They are sometimes called second integrals as opposed to first integrals. Sometimes they're called weak integrals, and there's a number of special integrals. Of course, the question is now, how do you find this c? Right? Because once you know c, then this is a linear problem. If you don't know c, it's not a linear problem. But before we get to that question, let's consider that the case where there are two Darboux polynomials with the same function c as cofactor. So then we have this p1 dot equals c times p1, p2 dot is the same c times p2. Then of course this ratio is going to be this, what we had before, and then p1 dot is cp1, p2 dot is cp2, so this is, the numerator is 0. So point is, if you have two polynomials with the same cofactor, then their ratio is a rational integral. So the idea of Darboux's idea is that you somehow find this c, and then you have you look if you can find two independent solutions of this equation here, and if you do, then you can have a rational integral. However, as it stands, if you don't know what the c is, and in general you don't, this is then a bilinear problem, because you can expand this c also, you know, with coefficients, let's say a, and the p1 coefficient is b. This is bilinear, and then once you've solved that bilinear problem, you know the c and the p1, then you can solve this one by solving a linear problem, because then you know the c. So in general, it's sort of twist and roundabout. It has some advantages over just trying directly to find a rational integral, particularly in low dimensions. There are lots of tricks in dimension 2, for instance, in particular, for what to suggest what this c might be. But in higher dimensions, it's pretty difficult. Now,
why? This should be a very basic question.
Yeah?
Why do you want to find a rational integral?
Excuse me?
Why do you want to find a rational integral?
Well, I guess first of all we should ask that to Darboux, but I guess polynomial integrals are easy to find, and the next easiest thing would be rational integrals. Of course, in general, but I thank you for your question. The point is, in our community we talk about preserving integrals, but actually to know what integrals the differential equation has, that's an unsolved problem. So the easiest thing is to find the polynomial integrals. This is a theory to find the rational integrals. And if they're not polynomial or rational, then really almost all bets are off. So that's sort of, it's the best we can do in a sense. So more generally, if you have two Darboux polynomials with different cofactors, then we have this simple but important result, that the cofactor of the product is the sum of the cofactors. So remember that. That will be important in the future. For the differential equation, the cofactor of the product is the sum of the cofactors. Okay, so now we come to the discretization of this idea. And so I should say, I call this discrete Darboux polynomials. Of course, the polynomials are the same, but this is just short for discrete this is just short for Darboux polynomials for a discrete system. Since I don't want to say that all the time, I just abbreviate that to discrete Darboux polynomials. So now we do two things. First of all, we instead of having a polynomial differential equation, we look at a rational map. And the reason being that polynomial maps don't really have many integrals in practice. And in practice what generally occurs are rational maps. If I mean that's or more complicated, but certainly not polynomial maps well, apart from things like Euler's method. Okay, so now we're talking about rational maps. So then we define P to be a Darboux, so I use the abbreviation dP for Darboux polynomial in this talk, to be this Darboux polynomial of the rational map phi if P of xn plus 1 equals C times P of xn. So the P's are still polynomials, but now the cofactor, if this map is rational, then you have to make the cofactor rational, otherwise it's just not going to work. So the difference before was that in the continuous case, P and C are both polynomial. Here P is polynomial, C is rational. And another thing is that I use this notation. The prime has nothing to do with differentiation, that it refers to a shift. Say instead of n, we get n plus 1. That's what the prime denotes. And again, of course, this means for x that satisfies this map, so you should substitute this in here. Okay, so then, of course, if you have two different p's that satisfy this same equation, you can just take their ratio, and then you see that the ratio of two of these Darboux polynomials is again a rational integral, rational first integral. And more generally, the cofactor of the product is now the product of the cofactors. I remember for the differential equation, the cofactor of the product was the sum of the cofactors. Here's the product. So you can think of one case, which is sort of, as a sort of the group, corresponding to a group, and the other to an algebra. This will be very important in what comes next. Oh. Yeah. Okay. So, and when I talk map here, among us, you should just think discretization of the differential equation, because that's what it will be for our purpose. But it also holds more generally for things that have nothing, maps that have nothing to do with differential equation, but I'm not going to talk about that today. So how is this going to help us find integrals of a given map? And if you ask, well, why do I want to know that? Well, when the differential equation has an integral, it's easy to check if the numerical discretization has the same integral. However, what I'm going to be interested in is the case that the mapping or the discretization has a modified integral. So it's not the original integral. Now, that means you should have to look for any function. So that's a lot more complicated. So that is why it's good to have some method to find what the integrals of the discretization are, these modified integrals. Okay, so how is this going to help us find integrals of a given discretization? The answer is in two parts. First of all, in the discrete case, we found a non-trivial ansatz for the cofactors. Now, for those of you that are not familiar with the term ansatz, it comes from the German course, and you might think of it as an educated guess, but one that is justified later on by the results. And as a matter of fact, this ansatz works in all birational examples that we have looked at so far. So I'll explain later on what birational means. And the other thing is, as I've explained, that in the discrete case, the cofactor is the product of the cofactor of the product is the product of the cofactors, and that will be crucial because that means in this ansatz, we're going to have a general ansatz where it's crucial that we can factor uniquely. Now, polynomials you can factor uniquely if you have a product of polynomials. If you have a sum of polynomials, there's no way you can tell uniquely what the original polynomials are. So it's going to turn out that actually the discrete case is easier here than the continuous case, which is quite unusual. Because of course generally a group is more complicated than an algebra. In this case, it's the other way around. Okay, so here's the answers. Don't worry too much about the details. The educated guess is that if you have a rational map phi with Jacobian determinant, J given like this, I've written it out in factorized form. Of course, sometimes, so these are the factors of the numerator, these are the factors of the denominator. Of course, sometimes there's just one factor, then it's easy. But so if there are a number of factors k in the numerator, we assume, we try for the cofactor, that's indicated by this C here, the same case, but possibly with different exponents. Where these exponents can be 0, or they can be the same as here, they can be higher than here, but it's just we know what the ingredients are. And it's just a finite number, because this is a finite number of terms, both in the numerator and the denominator. So it means that if we, because we will only go up to a certain degree, then this is going to be a finite number of cofactors. We just try each one of them. And so we have a finite number then of linear problems to find the Darboux polynomials. One thing I forgot to say, let's see how far I have to go back for that. If you look at this, and the same holds in the continuous case, if P of, say the locus where P of xn equals 0 is invariant. So if P of xn equals 0, then P of xn plus 1 is also 0, because something times 0 is 0. So that means that these are not like a first integral where you have a foliation, but this means that if you are on an invariant set where P is 0, you stay on that invariant set. So in the plane, for instance, these are the most simple case are just lines, or they could be circles or something like that. But it's not that the whole plane is filled with circles, it's just one individual circle that is invariant, typically for these second integrals, or Darboux polynomials. We'll see, I'll show you a picture in a little while. Sorry. Okay, so as I already mentioned before, the two main applications are in geometric numerical integration, and the other is in discrete integrable systems, which is sort of my other area. And I'm not going to be talking about that today. And actually there, this sort of idea of using the Jacobian determinant was sort of already in practice. But I guess it's in this area of geometric integration that this is a new idea. Okay, so I'm now going to come to part 2 of my talk, which is examples involving the Kahan discretization. So the first part of the, well, in 2.1 if you like, I'm going to explain what, or define what Kahan's discretization is. And then, time permitting, I'm going to do all these other things. First give a simple, these are all meant to be pedagogic examples. Of course we have much more complicated examples, but we have to sort of start from the beginning. So the easiest is a 2-dimensional example, then if I have time a 3-dimensional example, and then there's something which we're quite pleased about, that we actually also have a method to find if your system has some parameters, for which parameters there might be more integrals than in the generic case. And I think that's pretty novel, certainly in geometric integration. So all of this is, I have to say, is all this stuff about Darboux polynomials for us is only the last year and a half or something like that we've been working on that. Of course, we've been working on Kahan's discretization longer, but the connection is sort of a fairly novel idea. All right. So Kahan himself, he called this discretization unconventional, and I'll explain to you in a minute why. And in 1993 he wrote in an unpublished manuscript that I've used these methods for 24 years without quite understanding why they work so well as they do when they work. because sometimes they don't work. They don't always work, I mean. And if you count back 24 years before 1993, it means exactly 50 years ago this year. So it's the 50th anniversary of Kahan's method. In 2000, Hiroto and Kimura, these are two people that work in integrable systems, they independently rediscovered this method, applied it to some of the classic tops, classic mechanical tops, and so these were two integrable. Kahan was not specifically interested in integrable cases, but Hiroto and Kimura were quadratic vector fields, and they showed that the discretization preserved the integrability. That means, in particular, that it preserved all the integrals, or rather that there were modified versions of all the continuous integrals in the discretization. And then in 2011, that was generalized to a large number of integrable quadratic vector fields by Petrera, Pfadler, and Suris from Berlin. But again, there was not really a total explanation. And then after that, we have also worked on this Kahan discretization and found more and more systems and obtained gradually a better understanding of what was going on between our groups, between the Berlin group and I guess our collaboration. Okay, so this is William Kahan a few years ago. He's elderly now. And this is the definition of the Kahan discretization. So this is the most, I've written down the most general quadratic, this is the quadratic term, this is the linear term, this is the constant term, quadratic differential equation just in Rn. And then how do you discretize? Well, the left-hand side is standard, right? You do that for every, say, the Euler method, whatever. The constant also remains a constant. The linear term, you replace xj by xj, the old xj plus the new xj divided by 2. So it's like a midpoint rule. But this one is a bit different. The quadratic one, you discretize if you have xj times xk, then you do the new xj times the old xk plus the old xj times the new xk. And I guess the fact that the quadratic and the linear terms were discretized in a different way, that is why Kahan thought of this as an unconventional method. However, one of the first things that we found is that it's not as unconventional as Kahan thought, because it turns out that all of this can be written in the following way. Now you should think of x as a vector. It turns out that actually this is a Runge-Kutta method, restricted to quadratic differential equations. So Kahan's method is only defined for quadratic differential equations. We have since generalized this to higher order polynomial differential equations, but that's a more complicated story which I'm not going to talk about today. So I hope everybody can read this. So the Kahan's method is sort of like a combination of the midpoint rule and the trapezoidal rule, linear combination of those two. Push it up, sorry, yeah. Oh, it's behind it.
Reinout?
Yeah?
I mean, I would think if you said to somebody, can you come up with a time-stepping method for this, and make sure that it's don't have to solve any nonlinear equations, this would be the first thing most people would write down.
Thank you very much. Of course, if you look at this, this is defined for all vector fields, not just for quadratic ones. And for all vector fields, this is an implicit method. But if you look here, for quadratic ones, the beauty is it's implicit because there's the x primes appear here, but it's linearly implicit. So basically, you just have to solve a linear problem, which is just almost as good, well, more or less as good as being explicit. So it's going to be an explicit, rational solution. Actually, we have written it's something. Well, of course, now I'm going.
Time-dependent PDE. That's a very standard concept to write down a time-stepping method that's linearly implicit.
Yes. No, I know, but I guess Kahan. This was 50 years ago, and Kahan might not have been so aware of what was going to be happening in PDEs. No, this is good. That's right. We talked about this the other day, actually, right? Yeah. But
he also told us that he had a practical problem to solve, and he was just allowed to solve linear systems and not.
Well, that is right. So Elena and I actually met Kahan a few years ago and then discussed this with him and asked him, why he did it this way. And it turned out that he wanted to solve things on a pocket calculator, and pocket calculator 50 years ago. It was very important that it was linearly implicit and not fully implicit. And if it was explicit, then, well, he didn't get such nice results. Sorry?
I'm not sure we had pocket calculators yet.
Well, when exactly he said he had been using them for maybe they had in where he was. Okay, so now the script is going to get a little bit smaller. So this is my first example. This is a quadratic differential equation, inhomogeneous quadratic differential equation, just in two variables. And here, so here's just a reminder of what the Kahan discretization is. Now, here I've written it in this explicit form, so I've solved the linear problem. And so then you get a rational, and that's why we're are interested in rational, you get a rational expression in terms of x1 and x2. And this d is just the denominator, so that's in effect is the determinant of the matrix that you're inverting. Right, and that's just given here. So the first and second component have the same denominator, which is actually in all the examples here. So that's, remember that I talked about this ansatz, and I factorized the numerator, denominator. In this talk, the denominator is just going to be a power of this determinant d. Okay, then we calculate the Jacobian determinant. I hope everybody knows what if you have xi prime equals phi I of x, then the Jacobian determinant of this map, so this is a vector, is d phi I dxj. And so you can just calculate that, or compute that, calculate the determinant of that matrix, and factorize that determinant, which we've done here. And these, it doesn't matter exactly what these expressions are, just, you can factorize it and you get something which is not too horrible. It's just an h, of course, is a time step everywhere. Okay, so we see here that in this case the numerator has three different factors. So we're going to, for our cofactors, we're going to try k1 divided by d, k2 divided by d, and k3 divided by d. Of course, we've tried everything, but these are the ones that turn out to work. And here they are. C1 is k1 divided by d, C2 is k2 divided by d, C3 is k3 divided by d, C4 is the product of those three, which is the Jacobian determinant. And then what we do is we write down here, so that for each of these we solve this linear problem. Say p prime equals c times p, where p is the Darboux polynomial, and then these are the corresponding Darboux polynomials, and the notation is that p sub ij is the jth Darboux polynomial corresponding to cofactor I. So for this cofactor there's one Darboux polynomial, for this there's one polynomial, for this there's one polynomial, for this one there are two. So that means for this one we're in business, we can take the ratio of those two and that will be an integral of our two-dimensional map. And here it is, just this divided by that. I didn't mention that before, I think, but the Darboux polynomial is corresponding to the Jacobian determinant, they are actually inverse measures of the, or inverse densities of the preserved measure of a system. So in this case, well, you can take either this one or this one, but we take this one, and so 1 divided by this times dx1 dx2 is a preserved measure for this map. And so now we have all the results that we need for the discrete case, because we have an integral and a preserved measure in 2 dimensions. That's as much as you can get. And if we take the continuum limit, you see that these first 4 do not depend on the time step h. So that means that they are preserved, they are the same as in the differential equation. So the differential equation also has these Darboux polynomials. The last one, we take the limit h goes to 0, then this just becomes 1. And again, the ratio of these two is an integral of the differential equation. So that means that this divided by 1 is an integral, so it means this is just an integral. And similarly for the preserved measure, if you let h go to 0, it means just dx1 dx2 is a preserved measure. So just the standard area is preserved. So the area is preserved, and this function is preserved by the differential equation. That means our differential equation is Hamiltonian. And this is the Hamiltonian. So the way I've presented it now is that you start with a differential equation dx dt equals f of x, and I've pretended that I didn't know any of the properties of this differential equation. So I discretize it, I get x prime equals phi of x.
You know that f is quadratic.
Yes. Yeah, that is actually that's not difficult to spot if you see a differential equation. We calculate the Jacobian determinant and factorize it. So factorize j of x, and from those factors we use them as ingredients for the cofactors, and then we only have to solve linear problems. So we get the discrete Darboux polynomials of the map, and then take the continuum limit, and we get the dp's of the ODE. And so that's sort of the dream, that this may work, in many cases. Of course, yes, Robert.
So you start with this arbitrary polynomial p. Can you bound the degree of p ahead of time before doing any calculation?
Do you remember, Elena? I think maybe did Bambos look at something like. There's certain things certainly that you can do in the continuous case. And in the continuous case, because you're looking at polynomials, then if you're just looking at linear polynomials in 2 variables, you only need a few, and then you've got everything, because of course they form a linear space. And but in the discrete case, well, we haven't always got the analogs of those things yet, but I'm pretty hopeful that you can make, well, certainly some statements, but I wouldn't dare to make any precise pronouncements right now. Anyway, so the point is, so of course it is true, we go up to a certain degree. If the degree turns out to be much, much higher, then, well, we just run out of computer power, and it doesn't work. But barring that, the idea is simple. You just have solve linear problems. And the point is, this diagram does not commute, right? Because the analog here for the differential equation would be to take as, instead of the Jacobian determinant, to look at the divergence and see what cofactors add up to that divergence. But of course, anything, So one of them could be arbitrary, and then the other one would just be the divergence minus that. So it's that's just not going to work. Okay, so maybe let me first. Here is the picture of this system. Oh, I should have written down the. Maybe I'll go. I've got them here. Should have written down the Darboux polynomials. I'll do that now. I'll write that here. Okay, so I had P11 is x1 plus 3x2 minus 3. P21 equals x1. P31 equals x2. P41 equals x1, x2 times x1 plus 3 x2 minus 3. And so these are all Darboux polynomials for the continuous case and for the discrete case, but this is moreover a first integral so of the ODE. And these are the Darboux polynomials. So you see these three these three lines here. This one, this axis and this axis, they correspond to the second and the third one, and then this diagonal line, which is also invariant, that's this first one. When this is equal to 0, that's this line. The other ones are x1 equal to 0 and x2 equal to 0. And then in this particular example, which is an integrable case, the whole plane is foliated by these invariant curves, and they are given by where is it? This not being equal to 0, but equal to a constant, right? Because this is the first integral.
What equal to a constant?
This last, why that is?
No, you said it's this equal to a constant. I don't know what this referred to.
This expression. This is basically the Hamiltonian. So that can take on any values, and that's because we had this P42, which is 1 plus h squared times something, but that h squared disappears, so the ratio of these two is just going to be this.
Okay.
Yeah.
To stop you, why is the time step 117?
Yeah. These are the mysteries of the person that made this graph, which is my colleague, my colleague David McLaren. It certainly helps to have an integer, right? So you don't get any round of problems. I think I will skip this example for now because it's just sort of in a sense more of the same. I'll get back to it if I have time later on. Okay, so now I come to this three-dimensional differential equation which has two parameters, alpha 1 and alpha 2. So yeah, here I use x, y, and z instead of x1, x2, x3, but I'm sure you understand. So now we do Kahan's discretization, which means that if you have a product, you discretize it by taking the x in the new point times this in the old point plus x in the old point times this in the new point, etc. So you get this again, this linear implicit equation. You solve that for for x prime, y prime, and z prime. You get the rational map, which we call the Kahan map, which is a discretization of this. Then we calculate the Jacobian determinant, and we find that for generic alpha 1 and alpha 2, the map preserves this measure, so the x dy dz divided by x y z, and it preserves this linear integral, x plus y plus z. Now that's not very exciting, right? but in addition to that, and this is just using Maple, by the way. If the Maple can tell you also if there are special values of alpha 1 and alpha 2 where there are additional integrals. And it also gives you the formula. So I've got the table here. So these here we have the values of alpha 1 and alpha 2. And we see that for different values of alpha 1 or alpha 2, so there's actually 1, 2, 3, 4, 5, 6, 7, 8 special cases, and we get additional first integrals of the mapping, so of the discretization. So here you see, for instance, this is y times z divided by 1 minus h squared divided by 4 times x squared. Similar here. And then, of course, again, you can, if you like, take the continuum limit, and then you know what the integrals for the differential equation were. But that's not the only point. I should have mentioned also in the example that I had before, that you can look at these things two ways. You can I've presented it that we have a differential equation, we don't know anything about it, you can find its properties this way, but you can also say, well, I've got a differential equation that has certain properties, and which ones of these are preserved. So to come back to the previous example, we know now that it's Hamiltonian, that we preserve a modified Hamiltonian, which is actually this divided by this denominator, which was 1 minus h squared times something. And it preserves the three affine Darboux polynomials, which were x1, x2, and this affine term. And actually we have a general result, just as we have general results for Runge-Kutta methods. That is that Kahan's method preserves all affine Darboux polynomials of a given quadratic ordinary differential equation. So that's in any dimension. So it's not a coincidence that these three lines were preserved by the discretization. That's just a theorem that tells us that is the case. It's also not a coincidence that we get a modified Hamiltonian, because again, there's a general theorem, which is this theorem 3, theorem 3 here, that if you have a vector field with a cubic Hamiltonian, that means a quadratic, because you take always the gradient of the Hamiltonian, so you get a quadratic vector field and a constant symplectic or Poisson structure, then the Kahan discretization possesses two Darboux polynomials, both with the cofactor, the Jacobian determinant. And here they are written out. So this is in any dimension, any cubic Hamiltonian. So the example I gave was in 2 dimensions, but this holds in 300,000 dimensions, if you like. Of course, then the expression becomes very difficult, and you wouldn't be able to find them with Maple, but we've just got a general theorem that gives them. So of course, to say this is I guess our ultimate aim is not to do, say, to calculate Darboux polynomials for first one system, then another system, then a third one, a fourth, and do that, say, 100 times. We try to do this and get some idea of what the general underlying structure is and what the theorems are that give you solutions, say, of certain classes in arbitrary dimensions. But first you have to have a number of examples so you can spot the patterns that exist there. Yeah. All right. I was going to skip this one. I was here. So here we found, in this case, we found parameter values where there are extra geometric properties, if you like. And let me see what comes after this. Okay, so now have some things which I have not, or one thing that I have not written up yet, so I will do that on the board here. Because now I want to make a connection with the series of talks by Hans Munterkaas and Kourish Ibrahimi-Fard, and that is, it turns out, and this is part of this finding sort of, results that are more general, so that these aromas occur in this theory of Darboux polynomials as preserved measures. So now we'll take again as an example a simple quadratic differential equation. R squared. So it's even homogeneous, and then I guess the statement is, and I haven't given any proofs in the talk anyway, so I'm certainly not going to give a proof of this, but it's, once you know the result, it's not easy, it's not difficult to verify it. The Kahan map, so it means we apply Kahan's discretization. Our claim is that Kahan map preserves the measure maybe I'll write it here. The following measure, dx dy divided by g of xy, where this g of xy is given by the following expression, g of xy equals this is going to be the sum of two of these so-called aromas, or also you might say aromatic elementary differentials. By the way, this is the so-called reduced Nahm equation with icosahedral symmetry. So this has something to do with physics.
So these are now differentials of what? Of the original vector field?
Yeah. So if we define this right-hand side to be f of x, then these are the. So for those of you that don't remember this, for instance, this one means dfi dxj times dfj dxk and dfk dxi, with some summation over repeated indices.
It's the trace of the third power of the Jacobian.
Yeah. And this is a slightly more involved one. And that is not, and to our knowledge, this is the first, I mean, not this particular example, but the fact that preserved measures of the Kahan discretization can be written in terms, often can be written in terms of aromas. That's, as far as we know, is the first constructive appearance of these aromas, at least in numerical analysis, and possibly anywhere in mathematics. Because it's basically there's a beautiful theory about the algebra of these things, but they actually turn up in applications. This is a physical system. So, and of course we have more examples, but it's certainly at the moment it's not true that everything, that all the Darboux polynomials I've told you about can be written in terms of these. There's more going on, but certainly this is part of the story that is going on. And there was already, I mean, this is one of the reasons that people looked at these aromas in the first place, that there was an idea that this had something to do with volume preservation. Now here, actually, this is not standard volume which is preserved, this is a modified volume. Right? but still, there's a connection with measure preservation, indeed.
Could I ask?
Yeah?
But you find all the Darboux polynomials that are a finally equivariant, so that the mapping from the vector field to the polynomial is a finally equivariant. That's exactly what you find here, is it? By this approach? That's exactly what these series are describing. I mean,
if you ask if we can find all preserved measures that can be expressed in terms of Darboux polynomial, or in terms of aromas, yes, we can do that. But we also certainly we also find integrals that are, and that means also Darboux polynomials that are not expressed in terms of, expressible in terms of. So there must be something more, and we already have some idea of what that might be. And well, I'm sure that maybe this semester we'll figure it out. Hopefully. Yeah. All right. Let me see. I think I will leave some questions for some time for questions. So I will just go and wrap up. So here are some concluding remarks. We have found we've presented a method for finding first and second integrals and preserved measures. Of course, there are some other methods for finding integrals of discrete mappings. In particular, for integrable systems, there's a whole theory of Lex representations and so on. However, even then, even if there are other methods to find first integrals, our method also gives second integrals, it also gives preserved measures, and in some cases it gives more integrals than the existing methods. But in the case where there's no method to find first integrals, such as for Kahan discretizations, there was some sort of semi-heuristic way of finding it, which actually was quite successful, but it's certainly is unbeatable if you just have a linear problem, linear problem that you need to solve to find the integrals. That's written here. There's only linear algebra here. This is one of the things that. If you have, say several Darboux polynomials with the same cofactor, then you sometimes from these computations you get what would be for a human being weird linear combinations. So Maple doesn't give you the simplest basis often. So that there are some human. It's not that it makes a difference, but it just looks nicer than that you have a simple expression rather than a complicated expression. And then the computational issues, I've really sort of not paid much attention to that in the talk, but of course, if the number of variables becomes very large, or if the degree of the polynomials, the Darboux polynomials becomes very large, or if the parameters in the original system there are very many parameters, then that all makes it more difficult. And at some stage, our record, I think, is in terms of the number of variables, is something like what was it? 9 dimensions and degree 7 or something like that. That means, because basically, I haven't said this, but we try all polynomials, right? So that meant that of course, the space of polynomials is a linear space. So in the biggest system we've tried, this space has dimension 5,000 or something like that. So it's still linear, but that's sort of getting to certainly the edge of what you can do on a laptop. The other thing is, of course, that the equations for these Darboux polynomials have to satisfy are heavily overdetermined. So generically, if you just take a generic differential equation, it won't have any Darboux polynomials. So they're a little bit special. And then in some cases if we couldn't do it on the laptop, we've tried it on the supercomputer. Unfortunately, often that doesn't help a lot. You might be able to go 1 degree higher, and then if you're lucky, that's where the one missing Darboux polynomial that you're looking for is hiding. But there are also cases where in most cases actually it doesn't make a difference whether you use. There's probably also because our algorithms are not so refined yet. But at the moment, it hasn't made. Is this true what I'm saying, Ben? Is that fair enough to say that the supercomputer hasn't made a huge difference?
Yeah, it's very small.
A small difference. Okay. Yeah, I think that's it. All right. Then here are some references. First, references, of course, starts with Darboux, so more than 100 years ago. Then this book I can really recommend, and there's the section 2.5 is on Darboux polynomials. That's for differential equations, but that's certainly where we got a lot of our knowledge from. It's very readable. And then here in the audience we have somebody who, here they're called special integrals, but they're, if you like, non-autonomous Darboux polynomials. Liz has worked on that. Then Kahan's method, of course, starts with Kahan, this unpublished paper, which fortunately we do have a copy of. Then there was Petrera, Vater, and Suris that really started this in a big way. And then there's some of our own papers. And then here, this is the newest stuff. This has just come out like a couple of weeks ago. And this would be difficult reading for most people, I think. But they have some ideas of this for integrable mappings. Then here, discrete dynamical systems. Certainly here there's no systematic way for finding or for guessing the cofactors. So this is more, if you know that the discrete system has an integral, then you can calculate the rational integral, then you can calculate the cofactor. And then this is a sort of a follow-up to a paper here, which, is nearly ready, hopefully, to be submitted. So I will stop there.
Thank you very much for the interesting and very clear talk. We will ask the next speaker to set up the computer, and then we will have some short questions.
Yes, so any questions? Yes, Doug?
So I didn't get, you have the ansatz to look at things whose factors are factors of the numerator and denominator Jacobian determinant.
Yeah.
Why is that a reasonable ansatz? What's the heuristic?
Sorry?
What's the heuristic for that as an ansatz?
Well,
Everything is going wrong. Let me just, I'll worry about that later. The heuristic is that basically, I think we did some computation originally because we had a system for which we could not find the preserved measure. And then Brynjulf said, well, if we just compute them, because the preserved measure, with the preserved measure, there the cofactor is the Jacobian determinant, not some factor. So we just tried with the Jacobian determinant, and then we found preserved measure, but not just one, but we found several. And that was the start. And then, you know, as we went on with that, sometimes with this one cofactor, we found like a dozen different measures. And then the ratio of all of these is giving integrals. So that's really what started us thinking about this. And then later we found that sometimes you can get things a little bit more easily by looking at the factors of the Jacobian determinant. That's sort of in a nutshell how to. And now, sort of, you know, we've progressed more than a year. Now we actually have some proofs. Some of them I didn't present here, but that, for instance, for what I did, I didn't. But for instance, the linear Darboux polynomials, we have proved that in dimensions 1, 2, 3, and 4, they always correspond to a factor of the Jacobian determinant. And what I showed you for the the Hamiltonian, the modified Hamiltonian, they correspond to actually the Jacobian determinant itself. So we're now getting theorems where we have general results in, well, some in arbitrary dimensions and some in a few dimensions. And in principle, there's no problem in going to high. It's just we just do that by brute force. And then, so if you have a brute force, then you can go to higher dimensions. Yes, Sir Robert.
It's a bit weird that it's so heavily based on the Kahan map. Is that just because that's what you've chosen to look at?
Yes,
like
that is a very good question. It's just because that's what we've done most on, but this is true. So I have this whole other talk on integrable systems. It has nothing to do with Kahan map. It's exactly the same theory, except that there's no H there. Yes, Christian.
Well, if you're looking for preserved integrals, or if you're looking for integrals in the discretization,
Yeah.
In the examples you showed us, they were very nice because they converged against integrals of the exact equation.
Yeah.
But does it happen that you get spurious integrals, where if you send h to 0, they just diverge?
This is a very tricky question.
Or isn't that possible for some reason?
We have, so for instance, we have a method for discretizing cubic equations, which uses this polarization. But then if you have, say, a differential equation, a cubic differential equation in dimension n, the discretization is in 2n dimensions. So there you certainly do get things
You get
which,
spurious.
well, they're not spurious because they're different in the discrete case, but they all converge to the same continuous integral.
Okay, but you don't have to have some result.
Well, you certainly have spurious Darboux polynomials. These are things that come in from infinity, yeah.
Okay, so that just happens. I thought it might be prohibited because the method converges.
No. It is possible to have things coming from infinity.
I'm very sorry, but
I'm afraid that we will have to
Okay,
wait with
you
the
can ask me
questions
afterwards.
because- Yes, let us wait.